Hi everyone, this is Gasho again. This is section 3. In this section we are going to see solubility as an equilibrium process. Let's see the objectives. At the end of this section you'll be able to describe the distinctions among unsaturated, saturated and supersaturated solutions. The second objective is define solubility and describe the factors that affect the solubility of substances. Third objective is conduct an experiment to determine the solubility of table salt and sugar in water. This part should be done in the laboratory, so we are not going to deal with this one. The other objective is, so we are going to state Henry's law, and then we'll use Henry's law to calculate the concentration of gaseous solute in a solution. So these are the expectations, so yeah, I'm going to discuss them. Okay, now let's get started. Let's discuss about unsaturated, saturated and supersaturated solutions. Let's use the following hypothetical experiment to explain unsaturated, saturated and supersaturated solutions. Let's assume that you have this beaker. So you have 20 grams of salt, and then you dissolve it with 70 milliliters of water. So all the salt is dissolved. In this case, all the 20 gram salt in 70 milliliters of water at 25 degrees Celsius is dissolved. All the salt is dissolved. Now let's see another case. Let's take this solution and another 20 gram of salt. In this case though, only half of the 20 gram is dissolved. 10 gram is dissolved. The other 10 gram is undissolved. So you added 20 gram, 10 gram of the 20 gram is dissolved, the other 10, half of it is not dissolved. Totally you have 20 gram previously dissolved, you have additional 10 gram dissolved, you have total of 30 gram of salt dissolved in 70 milliliters of water at 25 degrees Celsius, and you have undissolved 10 gram which is settling at the bottom of the beaker, this one. Now let's do the next experiment. Let's heat this solution using a Bunsen burner. Let's warm it to 60 degrees Celsius. Let's assume that all the 10 gram, the remaining 10 gram over here, this one is completely dissolved in this case at 60 degrees centigrade. So all the salt is dissolved. Now let's slowly cool to 25 degrees Celsius without disturbing it. At this point 40 gram of the salt is dissolved. So initially, if you remember here, 30 gram is dissolved, but when you heat it to 60 degree centigrade, all the salt is dissolved. So we have 40 gram of salt dissolved in 70 milliliters of water. We slowly cool it to 25 degrees Celsius without disturbing it. Now we have 40 gram of salt dissolved in the solvent. Now let's explain what these three solutions are. The first solution is called unsaturated solution. Why it is unsaturated? Because it didn't dissolve the maximum amount of solute. It only dissolved 20 gram of salt, but this solvent can dissolve up to 30 gram of salt at 25 degrees Celsius. A solution that dissolves less than the maximum amount of solute that it can dissolve is known as unsaturated solution. The second type of solution is saturated solution. This one is a saturated solution. In this case, this solution dissolves its maximum amount. The maximum amount in this case is 30 gram. It can dissolve 30 gram at 25 degrees Celsius. If you add anything more than that, it settles at the bottom of the beaker. So this solution is known as saturated solution. A saturated solution is a solution that dissolves its maximum amount at specific temperature. In this case, say for instance 25 degrees Celsius. By the way, this is a dynamic equilibrium. This means at this point the rate of dissolution equals to the rate of crystallization. So still ions are going into the solution, and also ions are coming from the solution and crystallize on the solid. So the rate of dissolution equals to the rate of crystallization. So these two rates are the same. So at macro scale, at large scale, we cannot see any change. Even though at molecular level there are changes. I mean, there are still ions going into the solution. There are also ions coming from the solution and crystallize. These two rates are equal. So because of this reason, we cannot see any change at macro scale. At large scale, we cannot see anything. But still, these processes are going on at microscopic scale. A saturated solution is a solution that dissolves its maximum capacity. Let's come to the next beaker. So this solution is known as supersaturated solution. This is a solution that dissolves more than or greater than its maximum capacity. The maximum capacity at 25 degrees Celsius is 30 grams, but in this case at 25 degrees Celsius it dissolved 40 grams of salt. This kind of solution is known as supersaturated. You have extra 10 grams dissolved here, but at this temperature at 25 degrees Celsius the maximum capacity is 30. Anything beyond that makes it a supersaturated solution. So this is a supersaturated solution because it dissolved more than the maximum amount. So we have to be careful here because these supersaturated solutions are unstable. What does that mean? If you disturb the beaker or if you add a single crystal, it may induce recrystallization of the excess salt and probably it becomes a saturated solution. One more time. Unsaturated solutions are solutions that dissolves less than its maximum capacity. So the maximum capacity in this hypothetical case is 30 grams. Saturated solutions are solutions that dissolves its maximum capacity or its maximum amount. That is known as a saturated solution. A solution that dissolves more than this, more than the maximum capacity, is called supersaturated solutions. Supersaturated solutions are unstable. Okay. If you disturb them or if you add a single crystal, say for instance, this will induce recrystallization of the excess salt and then the solution becomes saturated solution. Now let's see the effect of temperature on the solubility of solids in water. So in this case we know that water is a universal solvent. You can use other solvents, but in this particular case we are going to use water as a solvent. So what are the effect of temperature on the solubility of solid in water? So we need to divide our solids into two. We need to divide the solids into two. One, gaseous solids. You may have gaseous solids. In general, for gaseous solids, if you remember, the gas particles are very far apart. Because of this reason, delta H2, which is the energy required to separate solid-solid interaction. In this case, for gases, it is 0 because the particles are very far apart. So this part is 0. This part is 0 means enthalpy of lattice is 0. So because of this reason, the enthalpy of solution for gases is exothermic. So what you'll have here is the enthalpy of solution for gases, since this is 0, right? We say that this is 0. Enthalpy of hydration equals to enthalpy of solution. Enthalpy of hydration is always exothermic. For exothermic processes in general, solubility decreases as temperature increases. They have inverse relationship. If you increase temperature, solubility decreases. So you can use this equilibrium system. In this case, if you increase heat, so heat should be added after the arrow. So you have a solid in gas, a solid in aqueous solution plus heat. This is for exothermic process. So you are increasing heat here. If you remember the Le Chatelier principle, what will happen is if you increase heat, the equilibrium will shift to the reverse direction, so that the gas will be bubbling out, which means its solubility decreases. So in general, for gases, as temperature increases, their solubility decreases. If you want to dissolve more gas, you need to decrease the temperature. So solubility of gases in water decreases as temperature increases because the enthalpy of solution is exothermic. In other words, the solubility of gases in water increases as temperature decreases. If you cool the solution, you can dissolve more gas. Okay, now let's see for solids. For solids, we can divide them into two. One, enthalpy of solution is greater than 0, which means the process is endothermic. For endothermic process, as temperature increases, solubility increases. For endothermic process, we usually add heat. Heat is added before the arrows. These are the arrows showing the equilibrium process. So in the case of endothermic processes, heat is added before the arrows, and then, which means if you increase temperature over here, okay, if you apply the Le Chatelier principle, the equilibrium will shift toward this direction, which means for endothermic process, the solubility of solid increases as temperature increases. This works for many solids, but this is not always true. The process may be exothermic in some cases. For exothermic processes, the solubility of solids decreases as temperature increases. In that case, heat is added after the arrows. So for exothermic processes, heat is added after these arrows. You are increasing heat here. If heat is increased here, what happens is this equilibrium will shift to the reverse direction. What does that mean? Their solubility decreases. For endothermic processes, as temperature increases, solubility increases. For exothermic processes, as temperature increases, solubility decreases. To dissolve more solids for exothermic processes, you need to decrease heat. You can dissolve more solids by cooling or by removing heat. Now let's see solubility. So what is solubility? Solubility is defined as the maximum amount of solute that dissolves in 100 grams of water at specified temperature. Maximum amount of solid. What does that mean? This means this solution is a saturated solution. So a solution that dissolves its maximum amount, we call it saturated solution. So when you talk about solubility, you are talking about a saturated solution. So that saturated solution in fact is in 100 grams of water. And the other point is, since solubility is affected by temperature, the temperature should be specified. So that's why it should be at a specific temperature. This is the definition of solubility. So now let's see solubility curves. This is directly taken from your textbook. As you can see, the x-axis is temperature, the y-axis is solubility, gram of solid per 100 gram of water. So how do you interpret this graph? Let's read this one, say for instance, sodium nitrate. This is almost close to 80. Let's say 79, say for instance. The solubility of sodium nitrate at 10 degrees Celsius is 79 gram per 100 gram of water. That's how you read this graph. So in general, as you can see from here, as temperature increases, the solubility of these solids increases, but the magnitude in fact varies from compound to compound. It's not uniform. Some of them are, the change is very significant. In other cases, such as sodium chloride, the change is very small. So in general, the solubility of solids increases as temperature increases. So let's see another graph. This contains gaseous solids. So in this case, if you look at sulfur dioxide, ammonia, and HCl, these are gases. So their solubility decreases as temperature increases. So if you increase temperature, the solubility goes down, the solubility of ammonia goes down, the solubility of HCl goes down. Okay. So solubility decreases as temperature increases for gaseous solids. For most solids, the solubility of solids increases as temperature increases. In fact, all these solids are dissolved by endothermic process. If it is exothermic, even though they are solids, their solubility decreases as temperature increases for exothermic processes. Now let's see the effect of pressure on solubility. So generally, pressure has significantly affected the solubility of gaseous solids, but does not have that much effect on the solubility of solids and liquids. The reason is that solids and liquids are incompressible. The particles in solids and liquids are very close to each other, so they are pretty much incompressible. But in the case of gases, the particles are very far apart. So if you apply pressure, you can decrease the distance between gas particles or gas molecules. So because of this reason, pressure has significantly affected the solubility of gaseous solids. Now let's discuss about the Henry's law. Henry's law states that at a given temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas over the solution. Let's explain the Henry's law using this example. So here you have, say for instance, the blue one is a liquid. So these are gaseous solids dissolved in liquid, and there is also gaseous solids above the solution. Henry's law says that the solubility of the gas in the liquid is directly proportional to the partial pressure of the gas above the solution. So above the solution you have this gas molecule. So if you increase the gas pressure or the partial pressure of these gaseous particles above the solution, their solubility increases. Their solubility in the liquid increases as the partial pressure of the gas above the solution increases. So mathematically, you can say that solubility of a gas is directly proportional to the partial pressure of the gas. Solubility here is the concentration of the gas in the liquid. This is directly proportional to the partial pressure of the gas above the solution. So this is the partial pressure. Partial pressure of the gas is talking about the one which is above the solution. If you remove this proportionality by a proportionality constant, it is known as the Henry's constant, Kh. So in that case, solubility of a gas equals the Henry's constant times the partial pressure of the gas. Okay, this is Cg is a concentration. The concentration should be in mole per liter of the dissolved gas. Pg is the partial pressure in atmosphere of the gas over the solution, the partial pressure of the gas over the solution. And Kh is the Henry's law constant. The unit is mole per liter per atmosphere. So now let's see this simulation. So if you compress it, what will happen? If you compress it, the gas, okay, more gas will dissolve in the liquid, more gas will dissolve in the liquid, and then equilibrium will be established. When equilibrium is established, you will not see any net change because the number of molecules leaving the liquid equals to the number of molecules entering into the liquid. So this is a very good simulation to understand how a dynamic equilibrium works. So this dynamic equilibrium can be expressed using this equation. So to indicate the effect of pressure, you can say that gas solid, you have a gas solid, you apply pressure, you have the gas solid in aqueous solutions. So in the case of gas, pressure is added before the arrows. So if you increase pressure, what happens according to the Le Chatelier principle? So what will happen to remove this effect? The equilibrium will shift to the forward direction, which means more gas molecules will dissolve in the liquid so that you'll have an aqueous solution. Okay, so that's a very beautiful animation that clearly shows you what happens in a dynamic equilibrium. The number of molecules leaving equals the number of molecules entering, so the net effect is 0. So in this example, calculate the concentration of carbon dioxide in a soft drink after the bottle is opened at 25 degrees Celsius under a carbon dioxide partial pressure of 3 times 10 to the power of minus 4 atmosphere. The Henry's constant is given, which is 3.3 times 10 to the power of minus 2 mole per liter per atmosphere. Let's see the given values. The given values, partial pressure of carbon dioxide is already given, which is 3 times 10 to the power of minus 4 atmosphere. The Henry's constant is given, 3.3 times 10 to the power of minus 2 mole per liter per atmosphere. Just the solubility of the gas is just the multiplication of these two. The required is the solubility of carbon dioxide in water. Calculate that, it just simply multiply these two. The Henry's constant, which is 3.3 times 10 to the power of minus 2 mole per liter, and partial pressure of carbon dioxide is 3 times 10 to the power of minus 4 atmosphere. Just multiply these two. In that case, you will get 9.9 times 10 to the power of minus 6. This atmosphere is cancelled by atmosphere, then what is left is mole per liter. So if you multiply this number with this one, you will get 9.9 times 10 to the power of minus 6 mole per liter. So this is the concentration of carbon dioxide in the solution. So this is pretty much a straightforward question. Now let's see another question. Now let's see this question. Fish need an oxygen concentration in water of at least 4 milligram per liter for survival. What partial pressure of oxygen above water in atmosphere at 0 degrees Celsius is needed to obtain this concentration? The solubility of oxygen in water at 0 degrees centigrade and 1 atmosphere partial pressure is 2.21 times 10 to the power of minus 3 mole per liter. First, let's try to understand this question. So what is given here? So the temperature is constant. In one case, when the partial pressure of oxygen is 1 atmosphere, the solubility of oxygen is 2.1 times 10 to the power of minus 3 mole per liter. In other case, when the solubility is 4 milligram per liter, we are asked to find the partial pressure of oxygen. That partial pressure of oxygen is very important because to survive, fish need 4 milligram per liter of water. So we are asked to find what partial pressure oxygen is needed to attain 4 milligram per liter of oxygen in water at 0 degrees Celsius. So we need to calculate the partial pressure of oxygen that is needed to attain 4 milligram per liter of oxygen in water at 0 degrees Celsius. So one concentration is given, which is 2.1 times 10 to the power of minus 3 mole per liter. That concentration is achieved when the partial pressure of the gas is 1 atmosphere. So let's assign this as CG1 and PG1. So the temperature is 0 degrees centigrade. Now in the second case, the concentration is given, but we need to convert this concentration into molarity. So to do that, we need to convert 4 milligram per liter to mole per liter. So just the first thing is you need to convert this milligram to gram, 4 times 10 to the power of minus 3 gram per liter. So you need to convert that mass into number of moles. Get the number of moles. We need the molecular mass of oxygen. The molecular mass of oxygen is 32 gram per mole. So if you divide it 4 times 10 to the power of minus 3 divided by 32 gram per mole, gram will be cancelled by gram, so it becomes mole per liter. You will get 1.25 times 10 to the power of 4 mole per liter. So this is the concentration. This is a concentration which is equivalent to 4 milligram per liter. So we are asked to find the partial pressure of oxygen that can give you 4 milligram per liter of solution. So we are asked P2. So what you are asked is partial pressure of the gas of 2 at this concentration. We know that from Henry's law, the equation is the Henry's constant times partial pressure of the gas. So if you rearrange this equation to get the Henry's constant, it becomes Kh is equal to the concentration of a gas divided by the partial pressure of the gas. So you'll have this equation. Similarly, if you do the same thing for the second concentration, for this one, you'll just rearrange this equation to get the Henry's constant. Just divide both sides by the partial pressure of the gas, 2, partial pressure of gas 2. So you'll get the Henry's constant equals the concentration of gas 2 divided by the partial pressure of gas at 2. So these two equations are equal because they have the same Henry's constant. So if you just arrange it in this way, these two equations are equal because this is just Henry's constant. So just we need to plug the values. If you plug the values, and this is the partial pressure of the gas, so you need to solve this. So just rearrange it. In this case, you will get 0.566 atmosphere. So this mole per liter will be cancelled by mole per liter. What does this mean? In order to survive, fish need 0.566 atmosphere of oxygen. If the partial pressure of oxygen is less than this, in general, aquatic life will be in danger if the partial pressure of oxygen is less than this value, 0.0566 atmosphere. Okay, now let's see the review questions to complete this section. The first question, it says, what will happen when a crystal of a salt is added to A, unsaturated solution, B, saturated solution, C, supersaturated solution? So as usual, just pause the video, give your answers. When you finish, play the video. So if you add a crystal of salt to unsaturated solutions, the crystal of the salt dissolves because the solution is unsaturated, it can dissolve more. And the second is for saturated solution. A saturated solution is a solution that dissolves its maximum amount. If you add a crystal to it, the crystal does not dissolve. In the case of C, supersaturated solutions are generally unstable. Even if you shake it or if you add a single crystal, that may induce the recrystallization of the excess salt, so that the excess salt will be converted to solid, and then that solution will be converted back to saturated solution. So this is how you distinguish unsaturated, saturated, supersaturated solution. If air contains 78% nitrogen by volume, what is the solubility of nitrogen in water at 25 degrees centigrade and 1 atmosphere? Henry's constant for nitrogen in water at 25 degrees Celsius is 7 times 10 to the power of minus 4 mole per liter per atmosphere. So pause the video and give your answer. When you are done, just play the video. So the trick here is the percentage is given. Percentage means parts per 100 in general. So if you have 78% of this total pressure, this is a total pressure is given, the percentage is given. So what you will do is you can just multiply this 1 atmosphere by 0.78 to find the partial pressure of nitrogen. This is 0.78 atmosphere, and then the Henry's constant is already given, so we just use the formula Henry's constant times the partial pressure of nitrogen. We have the partial pressure of nitrogen, just you plug them. 0.78 atmosphere times 7 times 10 to the power of minus 4 mole per liter per atmosphere. So this atmosphere will be cancelled by this atmosphere, so you will have 5.46 times 10 to the power of minus 4 mole per liter. So this is the solubility of nitrogen at 0.78 partial pressure. So this is how you solve it. The third question, the solubility equilibrium for the dissolution of carbon dioxide in water is shown below, and the enthalpy of solution is less than 0, which means it is exothermic. So this is the equilibrium. Carbon dioxide gas, then dissolved in water, it becomes carbon dioxide aqueous. So this equilibrium is given. The enthalpy of solution is 0. So use the Le Chatelier's principle to predict what happens to the solubility of carbon dioxide when the pressure of carbon dioxide is increased, the temperature is raised. Pause this video, give your answers. When you are finished, just play the video. So we know that pressure affects the solubility of gases. Pressure is usually added before the arrows. So if you increase pressure is increased here. Pressure should be added before the arrows, and if the pressure is increased, the equilibrium will shift towards this direction, right? What does that mean? More of this carbon dioxide gas will be dissolved in water. Okay, so the solubility in general, the solubility of carbon dioxide increases as pressure increases. In the case of B, the process is exothermic, which means we usually add heat after the arrows. Heat is added. Increasing temperature means increasing heat. So if you increase temperature, meaning you are increasing heat. If you increase heat, what happens? This favors the reverse process, which means the carbon dioxide gas will be bubble out, so that the solubility of the gas decreases as temperature increases, because as temperature increases, solubility decreases for exothermic processes. That can be explained using the Le Chatelier principle. So that is it for today. I'll see you in the next video.